Hello everyone and welcome back. In this video we're going to talk about an important theorem that is used in many results of this chapter, which is called the mean value theorem. Now in order to prove the mean value theorem, we will first need Rolle's theorem. Now Rolle's theorem has three hypotheses. First, the function f is continuous on the closed interval from a to b. Second, the function is differentiable on the open interval from a to b. And third, the function has the same value at a and b. So f of a is equal to f of b. Now, if all three of these hypotheses are satisfied, then this tells us that there is at least one c between a and b, such that f prime of c equals 0. So in other words, the slope of the tangent line at c is equal to 0. Now the figure shown on the left illustrates Rolle's theorem. So here we have a function that is continuous on the interval from a to b and is also differentiable. And the value at a and b are equal. So f of a is the same value as f of b. And so this tells us that there is at least one c that is between a and b, such that the slope of that tangent line at c is equal to 0. So let's take a look at an example for the use of Rolle's theorem. So let's prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. So in order to show that there's exactly one real root, we need to show two things. The first is that there is at least one real root. And the second is to show that there's at most one real root. Now to show that there is at least one real root, we will use the intermediate value theorem. So we're going to let f be equal to x cubed plus x minus 1. And now let's evaluate the function at 2 points. So let's choose 0. So we have x cubed, which is 0 cubed plus 0 minus 1, which gives us negative 1. So we know that f of 0 is negative. Now we need to evaluate the function at another point so that the function will be positive. So let's choose 1. So we get 1 cubed plus 1 minus 1, which will simplify to positive 1. So that tells us that f of 1 is positive. Now since f is a polynomial, we know that it is continuous. And by the intermediate value theorem, we know there is at least one c that is between the interval from 0 to 1, such that f of c is equal to 0. So it has at least one real root on that interval. Now to show that there is at most one real root, we will use a method called proof by contradiction. And the way that this method will work is to assume that the statement that we want to prove is false. In this case, what we want to prove is that there's at most one real root. So let's assume that this is false. So there's at least two real roots. Then what we want to show is that this will lead towards a contradictory statement. And then to resolve the contradiction, we will conclude that it was incorrect to assume that our statement was false to begin with, and thus the statement that we want to prove must be true. So for this example, let's assume that f has at least 2 real roots. And we'll call them x1 and x2. And since they are the roots of the function, that tells us that f of x1 is 0 and f of x2 is 0. So the function has 2 real roots, which we called x1 and x2. Now since f is a polynomial, it will be continuous and differentiable, and it satisfies the conditions for Rolle's theorem. We know that f of x1 is equal to f of x2. In this case, they are both equal to 0. So by Rolle's theorem, there is a C which lies between x1 and x2 such that the derivative at C is equal to 0. So this is the result of Rolle's theorem. And now let's try determining this value of C. So our function was x cubed plus x minus 1. And so its derivative is going to be 3x squared plus 1. And so by Rolle's theorem, it tells us that the derivative is equal to 0 at some point C. So now let's try solving for this point. We get that 3x squared plus 1 is equal to 0. So 3x squared is equal to negative 1. X squared is negative 1/3. So x is plus or minus the square root of negative 1/3. But the square root of negative 1/3 is not a real number. And so this tells us that f prime can never be equal to 0, at least for any real number. And thus we have a contradiction. And so what we assumed to begin with was that the function f had 2 real roots. And if it does have 2 real roots, it tells us that with Rolle's theorem, the derivative must be 0. But the derivative can never be 0. And so the statement that the function has 2 real roots must be false. And so f has at most one real root, since it cannot have 2 real roots. And since we showed at the start, using the intermediate value theorem, that there is at least one real root, this tells us that the equation x cubed plus x minus 1 equals 0 has exactly one real root. Now let's introduce the mean value theorem. Now this theorem has two hypotheses. First, the function f is continuous on the closed interval from a to b, and second, the function f is differentiable on the open interval from a to b. So this theorem tells us that there is at least one c such that f prime of c is equal to f of b minus f of a all over b minus a, where c is between a and b. So in other words, the theorem says that there is at least one value of c such that the slope of the tangent line at c is equal to the slope of the secant line that passes through the function at a and b. So the figure on the left illustrates the mean value theorem. Now let's consider the secant line, which is this dotted blue line, that passes through the points A and B. So now the mean value theorem says that there's at least one c, which is between A and B, such that the slope of the tangent line at that point is the same as the slope of the secant line, which passes through A and B. For this example, there are two values such that the slope of the tangent line at these 2 points is the same as the slope of the secant line. Now let's use the mean value theorem to prove the following theorem. If f prime of x is equal to 0 for all x in an interval from a to b, then f is a constant on that interval. So let's let x1 and x2 be any two numbers in the interval from a to b such that x1 is smaller than x2. Now since f is differentiable, on the interval from a to b, then it must be differentiable on the interval from x1 to x2. And therefore, because the derivative exists, we know that it will also be continuous on the interval from x1 and x2. So we satisfy the hypotheses for the mean value theorem. So it's continuous on the interval from x1 to x2 and differentiable on the open interval from x1 and x2. So that tells us that there is a c which is between x1 and x2 such that f prime of c is equal to f of x2 minus f of x1 all over x2 minus x1. Now since f prime of c, f prime of x is equal to 0 for any x, we have that f prime of c is equal to 0. And so this tells us that f prime of c times x2 minus x1, which will be equal to f of x2 minus f of x1. So we multiply both sides of the equation by x2 minus x1, and we know that f prime of c is equal to 0. So that tells us that 0 times x2 minus x1 is equal to f of x2 minus f of x1, and left-hand side is equal to 0. So this tells us that f of x1 is equal to f of x2. And x1 and x2 are any two numbers in the interval from a to b. That tells us that f is the same value for any two numbers on the interval from a to b. And so this means that f is constant on that interval. So now let's prove the following corollary. If f prime of x is equal to g prime of x for all x in an interval from a to b, then f minus c is a constant on that interval. So in other words, f of x is equal to g of x plus c, where c is a constant. So to prove the corollary, let's let capital F be equal to little f of x minus g of x. So now let's find the derivative. So f prime of x is equal to little prime of x minus g prime of x. And since f prime is equal to g prime of x for all x, then we know that f prime of x is equal to 0 for all x. And so by the theorem that we just proved, we know that f of x is a constant. So f of x is equal to capital C, where C is a constant. And so this tells us that f of x minus g of x is equal to a constant. So f is equal to g of x plus c. So that concludes our lesson for this video. In the next video, we will talk about how derivatives will affect the shape of a graph, and I'll see you then.